Thanks for having us today here. You can read the title of our presentation, helped by my colleague Sebastian and me. We are going today to address the topic of AI from a energy systems perspective, presenting two examples of the implementation of AI or things that could be framed as AI into our field, which is energy process engineering, and show you some aspects of our work at the FAU in Nuremberg. I'm going to start with the goals of our 20-minute talk, showing you guys what we are up to. We've first of all think that since AI is totally hot subject right now, we want to start why, in our opinion, modern energy systems might indeed benefit from certain AI methods and aspects. We will afterwards not able to dive very deep into the subject from a technical point of view, but we try to put the focus on the motivation of our approach and sketch the workflow that we've chosen from the engineering perspective and the potential benefits of these approaches. And eventually we want to motivate you or us to incorporate these methods of computer science into our fields, our toolboxes and workflows by using either well-documented or easy accessible tools, toolkits, or of course by boosting the interdisciplinary work within ABINET and collaborating with AI experts. So this very much defines the agenda for today. I'm going to begin for the first two bullet points, and Sebastian will resume from the second example on. So let's first take a look at the setting in which our work is embedded, which is the German. There has been a huge change in the German energy system over the course of the last 20 years. There has been an ongoing decarbonization, especially in the electricity sector. Around last year, 50% of the electricity was produced by renewable energy sources like wind or photovoltaics or biomass. Since there also were the political decisions to phase out the electricity production by means of coal combustion and nuclear power, this also means a shift from few large power plants to a network or a system of many distributed and decentralized energy systems. So we got many small plants or even domestic production. So we get a shift that goes in hand also with the necessity to increase the flexibility of the energy system, like things like in addressing load balance problems, address the intermittent energy production of the renewable energy sources, and also to implement energy storage systems or sector coupling options. So in short, there are plenty of things to do and to consider. We have a not very trivial task to do. We face challenges in the increased complexity of the energy system. We got an abundance of individual players and participants and stakeholders in this field, but also an increase in available data. And we also get, due to the liberalization of the energy market in Germany, more and more fluctuating commodity prices for electricity, for example. So this is actually a point where the energy sector is a perfect hotbed for the implementation of AI system. And it's not very surprising that it became so over the course of the last years. Regarding the energy or the electricity sectors, all major fields like consumption, production, trading, they offer tasks and options in which AI might lead to solutions or improvements in these fields. In the course of this talk, we're now going to look at two examples. The first one originates from the old energy world, like when we're going to present a workflow where we use a certain machine learning approach in order to optimize existing power plant infrastructure. And the second example, which will be presented by Sebastian, is an example in which AI is integrated already into the engineering workflow of process design and reactor development and the operation of novel energy systems. So starting with the first example, we're gonna take a look at existing biomass power plants. These are facilities in which we get several hundred, I think up to 500 in Germany. And all these plants currently suffer from uncertain economic conditions, economic pressure, and also expiring governmental subsidies. These plants produce electricity and domestic heat by combined heat and power production, typically running off chipped wood, typically material taken from forestry or landscape conservation materials. These plants' operational expenses are highly dependent on the fuel prices. So many operators will now and in future start buying and burning more and more cheap biomass fractions. Like we can see down here, there are different varieties available at different prices. The problem is, or the challenge is, that the operation has at all times to be emission efficient at high plant efficiencies, and of course stable and safe, which is not always easy with those cheap fuel fractions. In short, these low quality feedstocks require more specific and individual process conditions, which often are not possible to obtain in traditional environments of typical industrial control systems. The underlying control systems which these plants use typically run on very few PhD controllers, so very established technology, which influence only few process parameters like the fuel supply, fuel conveyor belts, or fans, ventilators for air supply. So the control loops, and this is even worse, these control loops are pretty slow and always reactive. That means that when fuel properties change during operation, we have to wait until the control system recognizes the changes in certain values, like different temperature in the combustion chamber, and will afterwards start to react and adapting the process settings. The idea that we get now is to introduce systems for fuel quality and load forecasting that would allow to know and set the process conditions which are beneficial for the operation in advance to the combustion process. So what we did is we developed a flow to determine the properties of the incoming feedstock, the quality of the incoming feedstock in advance by implementing a camera system into the plant. The plant, this camera system is approximately located around 30 minutes prior to the furnace, so all of the fuel passes the camera, and we're gonna take images or videos of the incoming feedstock. In the next step, image acquisition, image analysis techniques in order to characterize the images and correlate the information taken from the images with relevant fuel properties like the energy content of the fuel. In parallel to that, we also determine the optimal combustion setups for this very same feedstock, which is a typical engineering task in combustion engineering. And finally, we're going to use this information to affect the existing plant's control system by modifying like the speed in which fuel is injected or the amount of air that is introduced into the combustion chamber. This system, the advantage of such a system is that it can set up in advance or over a period of time. And when it's set up and trained and evaluated, it can react automatically. So it can go into a phase in which the system will continuously try to monitor and adapt the properties of the combustion chamber. So after introducing the camera, the most challenging step is, of course, the extraction of fuel properties from the image material. And we learned a lot on that subject during the last 2 years when working on different workflows of feature extracting and correlation techniques in order to access the image. What I want to do is just giving you 3 possible ways which we attempted to use, or which are we using right now, in order to access a property we call fuel quality or mixture rate in order to characterize the incoming feedstock. The first way is to use an empirical approach. That means we ask the plant's operator to characterize the fuel properties over a period of time as data. After we got enough plant data during our observations, we correlated the camera information with real plant data, operational data taken from the control system. And the third approach relies on image material, which we obtained in a lab scale environment under control. So we crafted such kind of a model, and we also implemented it into the boiler. And afterwards, we went into a learning and evaluation phase. We were quite happy to see that the model will show us deviations in the shown quality, and also nice to see that we found data which we didn't use for the training, but in our opinion is highly correlated with the fuel quality in the combustion chamber, which shows a kind of a similar behavior. So long story short, we also took then in the last step the process parameters which we think that are necessary in order to run the boiler with improved conditions, like the optimum of air amounts, or the combustion rate speed, or the amount of flue gas recirculation air, and closed the loop. So for around 6 months now, we got a industrial plant running with this setup in under closed loop conditions, which means that the process conditions are indeed determined by our camera system and not only by the PID standard process control system. We are currently in the phase of evaluation, economic evaluation of the setup, but we can already state that there is indeed an observable beneficial effect of the combustion behavior, and it could also be shown that stabilizing the biomass boiler's operation reduced the operational times of the peak load boiler, which is also situated at the same plant. This is marks the final part of my presentation. I think we gotta swap the screen share, and Sebastian will go on from now.
Okay, I guess you all should see my screen now. Starting from this very practical approach Thomas just told us, where we were able to implement our AI approaches in a real operating plan, we're now going to go to a bit more of emerging energy systems. But first, let us just still define the case in which we are. We're talking about, or imagining, an industrial player who wants to get his gas a bit green. So currently, this player just obtained natural gas from the gas grid, and it emitted CO2 while combusting this natural gas, basically for its process heat, for example. And it also realizes now that this is not only CO2 emissions, which might not be best for the environmental footprint, but they're also basically burning money because they need to pay for their emissions. And this is actually getting an issue now in times of rising CO2 prices. So their idea is to produce methane from renewable electricity. And this is the so-called power to gas concept, which you might have heard of. So basically, they're deciding to buy a reactor and put it on site. With this reactor, they can purchase green electricity from the grid. They can produce hydrogen, CO2 they're emitting to produce renewable methane. And with this methane, they can replace the natural gas they formerly bought from the gas grid. So now they are having 2 different ways of getting their gas demand fulfilled. The one is still purchasing natural gas, and the other one is to buy green electricity and produce the green natural gas themselves. But then there's of course a constraint for an industry player, because this operation needs to be to some extent economically feasible. They certainly don't just want to prevent CO2 emissions, but it also has to make sense from an economic point of view. So they only want to produce the renewable methane in those hours or in those days in which it makes sense for them. So this is quite a challenge, because when you're thinking of an operational player who's working on this task and who's defining on when to buy methane from the grid and when to produce it yourself, he or she is thinking of a quite tension field. Because on the one hand, we certainly need to think of the economic perspective, meaning natural gas prices, meaning carbon prices, which are the two cost components which might arise when we are using natural gas, but also electricity prices, which are the ones that need to be paid when producing our renewable methane. But of course, there's further restrictions, like the site-specific restrictions. Maybe there's a time-dependent CO2 availability, because the CO2 is certainly bound to the production processes in this industry. And maybe it's a batch process, so the CO2 availability is not in a steady state. And then also there's the gas demand, which might differ from time to time, because, as I said before, the production processes maybe are not steady. And this makes it even more complex. Then there's of course the technical perspective, where you need to know about what your reactor actually is capable to do. So first of all, we're having performance data like efficiencies, which might differ from certain operating conditions. Then there's things like load changes, maximum loads, etc. And most importantly, there's inertia that we need to consider. So we cannot just put on a switch and the reactor is working from 1 second to the other, but we are having certain startup times, we are having certain shutdown times. So when talking about such a reactor, we're speaking in the magnitude of 1 hour, for example. So we somehow need to know when to operate this reactor already in advance, so we can prepare the reactor for this operation. So all of those restrictions basically are time dependent. Prices are changing at the stock exchange, CO2 availability and gas demand are time variant. And also these technical restrictions force us to know about what's coming in those time dependent variables. So there's a need to forecast those developments. And this is where we are using AI in this project. So just to show you the very simplified approach, general approach of our model predictive process control in this case, and then we'll dive a bit deeper into where and how we use AI in this context. So basically, we are having the reactor. This one is really existing. It's in our lab at the FAU, and we first have a cost minimizing controller. So this is classic mathematic optimization, minimizing the overall costs. And it sends instructions on a minutely basis to the reactor. Instructions could be, for example, start heating up or start doing methanation with a volume flow of X. And the reactor is giving feedback to the controller to show the reaction of this reactor onto the instructions. Then, of course, this controller, to some extent, cannot just try and error things with the real reactor, but it should know what the reactor actually is capable to do. So we also integrated a reactor model, which you could call a digital twin if you want to, of this reactor. So with this reactor model, the controller can test different operating conditions and see if those might make sense and if the reactor is even capable of performing those. And then there's where we apply AI. It's in forecasting prices, demands, and CO2 availabilities. So prices is what we are predicting on a day-ahead basis. So we are predicting them once a day for the entire upcoming day. And then we are having the demand and availability, which is in the 2 hours ahead time horizon in a resolution of 1 minute. So those are operated frequently. And this one for prices is operated once a day in our model predictive control. To get a bit deeper on how and why we use AI in this concept, we'll just have a look at those prices, and we take the example of electricity price forecasting. we chose artificial neural networks to do those forecasts, and there's a few benefits which led to our decision to choose those artificial neural networks. First of all, the pricing mechanism on the electricity market is quite complex and it's heavily nonlinear, and this is a point where artificial neural networks are quite capable to deal with those. Plus, it's relatively easy to implement those neural networks compared to if you want to have an electricity price model which is considering all the fundamental correlations between the different input parameters, and being so is computational, relatively inexpensive, which is especially important for those neural networks which are predicting the availability of CO2 and demand, because they are executed on a minutely basis. And then the neural networks are capable to deal with a multitude of determinants. So, for example, we can use inputs like day and time data as a proxy for renewable, and feed in load commodity prices such as gas, CO2 prices, and also power plant availabilities. For example, if you have large parts of the nuclear power plant fleet which are unavailable due to maintenance, this certainly has effects on electricity prices, and you can consider all those prices, basically all those things basically, or try to consider those with the neural network. To show you how this works and that it works, I prepared two small examples for you. The first one is a very, very easy, very simple artificial neural network where we got only a very few inputs. Inputs is basically just electricity prices of yesterday and 1 week ago. We know the hour and we know the actual date. So basically the electricity prices just knows about its autoregressive part in the past. And when we are having such, I would just call them textbook electricity prices. Those are the real electricity prices. I call them textbook because when you would read a textbook about how do German electricity prices look like, then you would get such a graph, because you're having this morning peak, you're having the evening peak, you're having a decrease during night, and you're having a decrease during the day because of PV production, and this over days and days and days. And in such situations, this very simplified and very, very easy artificial network is able to predict the time series quite well. But if we have a look at other weeks, like for example this, where we had a very high infeed of renewable electricity sources here, which led to negative electricity prices in some hour, we see that the network really fails in explaining those or in predicting those parts here, those hours. That's basically because it has no clue about the real determinants of such hours and of such prices. But what you could do now is to just give the network a few more information, meaning you give it more inputs. And that's what we did. We added, for example, load data of yesterday and then the week before. We added the predicted load of now. We added what renewable feed-in is predicted for now, which gas price is predicted, and also, as before, electricity prices and the actual hour and the actual day. And if we're looking at those textbook prices, we are able to predict them quite well as well. But I mean, we were able to do this with the easy or a simple neural network as well. But looking at this tougher period, I would say, then we can actually predict those spikes, I would say, approximately well. Of course, there's some hours in which we overestimate the price drop, for example. But compared to what we did in this purely autoregressive neural network, results look quite well. And we certainly such forecasts and such inputs, because otherwise we will not be able in our model predictive control to optimize our operation from an economic point of view. So this was the example of our model predictive control in this power to gas system. I would like to finish now with a short summary of what we tried to discuss so far. And maybe let's come back to our title, which was a bit which was a bit interesting because we asked ourselves, are they smarter, better, and cheaper AI in energy systems? And when looking at existing energy infrastructure, with the example of what Thomas told us, actually AI are a mean to make those infrastructures smarter, because the power plant now starts acting instead of just reacting. Is it going better now? Well, yeah, one could say, because the biomass and gas consumption in this plant decrease. And is it cheaper? Thomas' calculations showed us that there's OPEX savings possible of up to 30%. For emerging energy systems, the question smarter, better, cheaper is maybe not the right one, because it's even more. AI in such systems is one of the prerequisites to operate such systems in an economically feasible way. So it's not making an existing system better, but it's enabling a new system with AI. But of course, all the examples that we showed you now, where we used AI, maybe could also be solved with other methods of statistics or whatever. For example, of course, there's other ways to predict prices than AI. So we would like to call AI not the universal remedy for the energy transition, but it's rather one element, in our point of view, to increase the efficiency of existing infrastructure and to promote emerging energy systems. With those words, I would like to close our presentation now. And of course, we are very much looking forward to hearing questions and answering them.